Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is Lecture 5, Part 1, and Video 13. So far in this section, we have reviewed the properties of expectation, covariance, and variance. We've discovered what the likelihood function is and how to use it to find maximum likelihood estimators. And now we are going to review the properties of logarithms and see a usually easier way to find the MLE using the log likelihood. That's going to be the log of the maximum likelihood function. So let's get started. Last time we talked about the likelihood function, and we used the likelihood function and the derivative of it and we set that equal to 0 to find a maximum, and then we had to check it, and we wanted to make sure that so we wanted to check it, and I said that you need to use the first derivative test because the second derivative test is going to be a nightmare. So that is what I'm going to assign you as one of your homework problems. I've given you the equation here, and you need to use this, and you can convert these sum of xi's to x bar if you want, n x bar, right? So this is n times x bar. You're welcome to do that. That means that in this one place you can factor out the n's, and that should simplify your calculations again. Remember that in this case, x is just a constant. P is your parameter. So I want you to take the second derivative, so take the derivative of this. Make sure that you use your product rule. This is going to be messy. I want you to show all the steps and all your work, and I want you to factor out the common terms. So you should get this in the nicest form that you can. So you're going to have to be very careful. Remember, because you have 3 terms here, you're going to have to use your product rule twice. Okay? So you're going to have to group 2 of these together as one term. That's one way to do it. Okay? So you might want to choose the easiest one, or there may be another method. So that's up to you to find and figure out. But that's going to be one of your homework problems. So have fun with that. A little calculus should help you get your skill back with calculus. All right. So again, the reason we're going to go over the properties of logarithms is it may have been a while, and you need to use them correctly so that you can do these problems easily. Using logarithms, the log of the likelihood function is what we usually do, and it makes everything so much easier if you do it properly. So you need to know these properties to be able to do this well. So in statistics, we rarely use anything other than, as far as logarithms, we don't really use anything other than the natural logarithm. So log x is going to be the same as ln x, okay? Because it's a log base e. So when you see in a statistics text like this log, I mean log e, the natural log. But I am not going to write ln, okay? It's easy. It's harder for me to write ln than it is for me to write log, so I'm going to write log, okay? Now, so let's think for any logarithm, log of a times b is equal to the log of a plus the log of b. The log of a divided by b is equal to the log of a minus the log of b. And these should have been proved for you a long time ago in algebra. And the log of the log of a constant raised to an x, so this is a constant, raised to a variable, x, is simply x times the log of the constant a. If I take, since this is log base e, if I take log of e to the a, that's going to be just a. Likewise, if I take e to the log of a, because this is log base e again, I get a. So these are I don't think these are usually covered very much, but those do come in handy in this course. So the log likelihood function is simply the natural log of L of theta. So I write this as little l of theta. I don't think your textbook does, but a lot of textbooks use this notation, and this is so much easier than writing this every time. Okay? So I'm going to use little l of theta for the log likelihood function of theta. And it's often much easier to do this, to use this to find the value of theta that maximizes log of L of theta than it is to try to use capital L of theta, the likelihood function. Okay. I want you to know that the log function is strictly increasing. In fact, here is a graph of the log of theta. So theta is along what would normally be our x-axis. Remember that when theta is 1, log of 1 is 0, because remember, log of base b, 1, equals, I'm going to say x. This is identical to b to the x is equal to 1. And we can't have a base 0, so that means b is not 0. What value of x makes b raised to that power? 1. That's 0. So b to the 0 is equal to 1. So therefore, log 1 equals 0 for any base b. Okay? All right. So that's why we have this graph here. And when theta is less than 1, log is negative. And when theta is greater than 1, log is positive. It's strictly increasing. When it's strictly increasing, there's a theorem in calculus, and it's so as long as L of theta is not equal to 0, so then the solution of the log of the derivative of the log likelihood function, which is the log likelihood function. So the derivative of this equals 0, and the derivative of this equals 0. They're the same, okay? So the solution of these for theta is the same for these, because this function is strictly increasing, all right? So the only time we have problem is when we have the log of when L of theta is equal to 0. That's a problem. So for this, but we'll know if we run into that, we'll have to revert back to just using L of theta. Okay. But remember, when L of theta is equal to 0, L of theta equal to 0 is not a maximum. Not really. Because if that's the largest value that L of theta can take, then everything is 0. All the probabilities are 0. The PMFs are 0. So that's not a very interesting case. All right. So here is something you need to know. That if I take the derivative of theta with respect to the log of theta, then so first I have, here is my quantity within the function. So remember that if I write this as natural log, if I say d dx of ln x, that's going to be 1 over x. And then by the chain rule 1, I take the derivative of this. So now if I have d theta of log L of theta, I take, this is going to be 1 over L of theta times d theta of L of theta. Okay? And it can be rewritten as this. So we take the derivative of L divided by L. It's always going to be this, if you want to remember that. Okay? So that's up to you. I just take the derivative myself. Okay? So it's so easy that I just keep taking the derivative. But you can remember that. I've put that in there so that you can do that quickly each time if that's what you want to do. Okay? So unless I say show the derivative, you can use this formula. All right? Now, here I want to here's L of p, and I want you to give me little l of p. So you're going to have to take the log of this. Okay? So this is going to be the log of the whole thing. P sum of xi, 1 minus p, n minus sum of xi. And so this is a term, they're multiplied by each other, so there's going to be a sum here. Log of p to the sum of xi plus log of 1 minus p to the n minus sum of xi. And using my properties of logarithms, this is going to equal sum of xi log p plus n minus sum of xi, please use your parentheses, log of 1 minus p. If you don't use your parentheses, I'm going to consider it wrong. And it's certainly sloppy. So please use your parentheses where you're supposed to here. Okay? I don't have to use parentheses here because I only have one thing in the log. But here, if I didn't use my parentheses, you wouldn't know if this is log 1 minus p, log 1, and then quantity minus p, or if it's log of 1 minus p. So use your parentheses. Same thing's true here. Okay? So please don't be sloppy. You need to be thorough and make sure that no one can be confused with what you've written. So here is my log likelihood function, okay, from example 1. Now let's do another example. Let x1 to xn be a random sample from an exponential distribution. So now we're going with a continuous distribution as far as x, but it's really not going to matter too much. We're going to do the same thing as long as p is not discrete. If p is discrete, we go back to the first part of example 1, and if p is continuous, that's usually what we're going to focus on in this chapter, but not always. All right. So the exponential distribution with PDF, f of x theta, and remember this is 1 over theta e to the negative x over theta as long as x is 0 or larger and it's 0 otherwise. And now it's important for us to put our parameter space in there, and so we write that in set notation, so please do that. So sigma is equal to the set of theta such that theta is between 0 and infinity. Theta is not 0. Okay? So for the exponential, theta equals 0 is not a case. So the first thing we want to do is we want to find the likelihood function. Okay? So let's see, this is example 2. I want to make sure that, oh yeah, so example 2. Now, we want to find A. I want to find L of theta, and remember that this is the product from I equals 1 to n of f of x theta, which in this case, you can skip this step if you want, as long as you do it correctly, all right? This is I equals 1 to n of 1 over theta e to the negative xi over theta. Make sure you use the I for xi, or else you're not gonna get the right answer here. Okay, you have to put in the xi, even though they're IID. We want to keep x1 separate from x2, etc. And so when I multiply these, 1 over theta is a constant, so this is just 1 over theta to the n. There's n of them. 1 to the n, but 1 to the n is 1, and so I'm left with just 1 over theta to the n. Okay, and this is how I want you to write it. Okay, so 1 over theta to the n. If you don't do this, it looks like your math skills are rudimentary, and we don't want that. We want you to look good. Okay, and then I have all of these exponents that I need to add together because it's e raised to the xi over theta. So this is going to be e to the negative sum of xi divided by theta. Okay? And then this is going to be for theta, because it's a function of theta. Theta is greater than 0. All right? So this is sigma, right? Not in set notation, but it'll do for this. So that's the answer to A. All right? You need this as well. Okay? So it's this is the solution that I've underlined. So give me the whole thing. B, I want L of theta is simply the log of this. I'm not going to write the log. I'm just going to do it. I've got two terms here. I've got this one and this one. And I'm going to use, I'm going to have a sum of logs because this is multiplied. Okay? So this is equal to log of 1 over theta to the n plus log of e to the negative sum of xi over theta. Okay, and this is equal to, okay, I've got log 1 minus log theta n, That's the first term here. And then I've got plus the negative sum of xi over theta quantity log e, which becomes 1, or you can use our property that we went over and you could just know that it's this whole term is this, okay? If you just write down this whole term is this, I'm okay with that because I gave you that property, okay? But I showed you how you could do it a little longer way here. Now log of 1 is always 0. So I'm left with, and now I've got negative log theta to the n right here. So that means I can make that n log theta. Don't forget your minus sign. So minus n log theta. And then I have plus times a minus here. So minus, I'm going to put theta to the negative 1 sum of xi. Okay, so that is part B here. And again, theta is greater than 0. So this is my solution right here to part B. Okay. C, I want to find the MLE. So now I say L of theta equals 0. Remember, that's going to give you the same solution for theta as if if the likelihood is set to L prime of theta is equal to 0. That's the same solution if you take the derivative of the likelihood and set it equal to 0. Okay. So I need to find L prime of theta. So remember, it's with respect to theta, not x. So I've got negative n times 1 over theta, and then by the chain rule, d theta is 1. You can put that in there if you want. Shows that it'll remind you to use the chain rule. And then I've got minus, the sum of xi is a constant, so I can just pull it out to the front, and then I need to take the derivative of theta to the negative 1. So I'm going to have negative theta to the negative 2, and then the derivative of what's in the function here, which is theta, is just going to be another 1 by the chain rule. Okay? So let's see what we've got. Simplify. So we've got negative n theta to the negative 1. You don't have to write it this way. That's up to you. You can write it as 1 over theta if you like. That's just a preference. And then I've got a negative and a negative, so this is going to be plus, and so this is still minus. Don't forget your minus sign out here. And so this is going to be plus, I'm going to write theta to the negative 2 sum of xi. That way I don't have to worry about if it's xi theta in the summation or not and use extra parentheses. I'm going to avoid that. And then I'm going to set this equal to 0. All right. So by setting this equal to 0, what I need to do is I need to, I want to get theta by itself, so I want to, what I'm going to do is I could write this as n over theta, negative n over theta, plus sum of xi over theta squared equals 0. And I want to get theta in the numerator. The safest way to do this is to multiply by the largest exponent on both sides of the equation. So this implies that 1 over theta squared times negative n over theta plus sum of xi over theta squared is equal to, I'm sorry, not 1 over theta squared, it's theta squared. Okay, sorry, let's be careful there. So I want to multiply theta squared because I want to get it out of the denominator. So I need to take and multiply by that on the top. So negative n over theta plus sum of xi over theta squared equals theta squared times 0, which is still 0. So this gives me negative n theta plus sum of xi equals 0. Okay? So that is the probably the safest way to do that. And then we end up with, now we can solve for theta. We can have n theta equals sum of xi implies theta equals x bar again, sum of xi over n. Okay. Now we need to check if this is a max or a min. And so so I'm going to, now I can easily take the second derivative with respect to p. I'm going to make sure that I use, I'm going to use this format here. That's why I wrote it with the negative exponents. I'm going to use this here to take the derivative. Okay, the simplest form of the derivative. So I'm going to take the derivative of that. So I'm going to get, it's with respect to theta. So the first term, I'm going to have a negative 1 times a negative n, if you want. Theta to the negative 1 minus 1, so negative 2. And then I'm going to have, I take plus, but I have a negative 2, theta to the negative 3, and then sum of xi is a constant. And so this I need to simplify. I've got two negatives in the first term. That becomes theta to the negative 2 minus 2 theta to the negative 3, sum of xi. Now, I want to plug in x bar for theta. Okay, so I left out my n here. Don't want to leave out your n. So this becomes a positive n in the front here. And then minus 2. Okay, so I can rewrite this as n theta to the negative 2, or actually I'm just going to put it on the bottom now, equals n over theta squared minus 2, and I'm going to say n x bar over theta cubed. So I multiplied and divided by n times here. So n over n, sum of xi equals n times sum of xi over n, which is x bar here. So that's what I'm doing again. That's the little trick I'm using. And that'll make it easier. If I put this in terms of x bar whenever I can, it'll make it easier when I plug in, right? So now I need to find, this implies L of x bar is equal to n over x bar squared minus 2n x bar divided by x bar cubed. I can simplify that. So I have equals n over x bar squared minus 2n over x bar squared. They have a common denominator. I have negative n over x bar squared, which is less than 0. Therefore, x bar maximizes L of p, of, theta. So theta hat equals x bar. That is my answer now. Let's pick up here. This is an extra optional example. I will make that a supplemental video, and then we will pick up with example 4 for the normal distribution next time. Update your formula sheet if you need to. If you have questions, come to virtual office hours. If you can't do that before you need help, then email me. I am happy to help you with course content. Take care of yourself, stay safe, and we'll see you next time.